All right, so our first problem, what is your challenge? We are starting out and we're going to go ahead and dive in with our first problem with a query that has joins in it, because most of the time we are in fact having to create an index for a query that often is quite complicated. Now, our sample query just has one join in it, but sometimes we're looking at a query that has, in fact, often we're looking at a query that has 2 joins or 3 joins or more than that. Maybe it has subqueries in different parts of it. This means when there's multiple tables in there and there's multiple joins and there's different where criteria and there's maybe subqueries, it can be really, really hard to figure out, okay, with all of these different things I could index, where is the most likely the place that indexing will pay off? Because just because I could create indexes on all these tables, it doesn't necessarily mean it's going to matter to the query. So in our first problem, we are going to figure out a lot about how to decode that. Now, one of the things that seems like it would be a great idea is to look for these little green hints that can appear in a query execution plan. Now, they appear in 2 places. The hints appear in a query execution plan, but they also appear in these missing index dynamic management views. DMVs up here stands for dynamic management views. They're also functions. So it's, some people say DMVs and DMFs. Same thing, they're these built-in tools that help suggest where indexes should go. You also see them as this little green hint at the top of execution plans. Now, the problem with this is it doesn't always suggest the best places for you. And it might have multiple suggestions, but the little hint in the plan only shows you one. And then if you're looking at the dynamic management views, it doesn't include the query that's related to the index request, because there could be in these dynamic management views, it's aggregating all of the suggested indexes. There could be many different queries that feed into a single request. And so it's very, very difficult. And we'll see how those can be misleading. We'll see examples of those today and tomorrow. So our problem in this first one is to figure out how to see through some of the complexity. And this one, we've just got one join, and figure out what is the most important index for this query. So our mission is to design, we can only design one single column non-clustered index. So the perfect index for this query may have multiple columns. Maybe it has included columns, but we're just going to say, if I can just pick one column to index, I want to pick the single column that's going to speed up this query the most. And how will we measure how well it does? We are going to measure how many logical reads it does. So when SQL Server is using these disk-based indexes, it will count up how many physical pages did I have to read. A physical page has 8 kilobytes of data on it. SQL Server stores data for these disk-based row store indexes in 8K pages. So we want to know what index made it have to read the fewest number of these pages. And I'll show you how to measure them as well. Now you might say, okay, to get the absolute best index, I'm just going to truncate the table, because if I remove all the data from the table, yeah, it will have 0 logical reads. Now, it's not really the challenge, but I appreciate your ingenuity if that's exactly where your mind went first. Yeah, we're trying to, on this one, no changing the query. We're just designing a single row store B tree index without any fancy things and without truncating the table. Here is our query. Now, your challenge is to design the best single column index, just one for this query. Our query is looking at 2 tables in the sample Babby Names database. This sample database has census data, or not census data, it has Social Security data from the United States government, and it collects all of the names of babies, and they have names going back to 1880. They publish this data in just data dump files, and I have imported them into a SQL Server database. And we're looking at a table named ag.firstnamebyyear that's aggregate level data. That's actually what we get from the government. So for example, it will say for the year 2017, there were 5,000, I don't know if that's correct, but 5,000 female babies named Kendra, right? We don't get one row per Kendra. We get, for this year, for this gender, for this name, there were this many babies. And so this table contains information on the gender, name count, and report year, as well as for each baby. In fact, that's it. It's the report year, name count, and gender, because name count is the count there, for babies going back to 1880. But I have normalized the data a little bit. The ag.first name by year table, which we've aliased as FNBY, it doesn't have Kendra written out for all the babies named Kendra because character data takes up a lot of space. So I have normalized it a bit, and it just contains a surrogate integer called first name ID. So the name Kendra, I have a table that's called ref.firstname. And ref.firstname, it just has a unique list of all of the baby names. It assigns a 4-byte integer to that baby name. That is the first name ID. And then it has another column that says, oh, for the baby whose integer is, and again, I haven't memorized the one for Kendra, maybe Kendra is 80,292, that translates to the character value of Kendra. So to decode this name data, I have to join from ag.firstname by year to ref.firstname on that first name ID column, because I actually only want information about certain names. In fact, one name and one gender. This query only cares about babies who are named Taylor, and we have to put that predicate against the ref.firstname table, aliased as FN. But then we only want Taylors. I mean, Taylors could be boy babies or girl babies. We only want information back on the girl babies. And that gender column is in the ag.firstname by year table, aliased as FNBY. So going back, I'm just cleaning off everything I had. Our challenge here is we've got a lot of stuff that's going on here to filter things. We've got a join here between the two tables. We have two predicates here that are filtering out rows. Our task is to figure out what is the column that is going to have the most payoff to index. Well, let's zoom out a little and look at these two tables. The ref.firstname table, we are joining on that first name ID column. And we are saying, okay, we only want babies with the first name of Taylor. Taylor is varchar 255. And our query is being consistent with that, right? We don't have a little Unicode symbol here. We are using the correct, this is going to be implicitly converted into a varchar thing. So we are matching, for the first name, we are matching the appropriate data type because this isn't Unicode data. If you don't know what that means, don't worry about it. You don't have to worry about any data type mismatches is what I'm trying to say. We are joining the two tables on first name ID, which is an integer in both tables. Those data, it's important to do joins on the right data types too, and we are doing that. And then, so that's our join between the two tables is on this. We have a predicate on first name, right? We only want first name equals Taylor, and then we have a predicate on gender. We only want gender equals F. And again, we don't have a data type mismatch on that as well. The ref.firstname table, it does have a clustered index. In other words, the data itself in the table is a disk-based row store index ordered by that first name ID column. So everything in ref.firstname is already sorted by first name ID. So first name ID 1, 2, 3. The data itself in the table is ordered by that. We have a more interesting key on ag.firstname by year. We have a clustered primary key on, and this is the order it's in. It is ordered first on report year, then on first name ID, and then on gender. So this is a composite clustered primary key. Because it is clustered, the data itself is ordered by these three columns. And the fact that it's a primary key means that, and both of these are PKs, it means there's a business rule that says we can, for each combo of report your first name ID and gender, there can only be one unique combination of those values. So for all the the baby's named Kendra, born in 2017, right? For 2017, and then that integer number that's a surrogate for Kendra. And for girl babies, there can only be one row for those. It must be a unique combination. Now, of course, for the boys named Kendra, and we do have some records of the boys named Kendra, there can only be one row for a given report year, that first name ID and gender for them as well. So everything is ordered first. The primary sort order is on report year. So all the 2017s are together. And then after, when all the 2017s are together, the secondary sort order for the rows in 2017, it's then first name ID 1, first name ID 2, first name ID 3, et cetera, et cetera, et cetera. And then if we were to have 2 rows for first name ID 1 for 2017, and maybe we would, because maybe that's a name that has boys as well as girls, then they will be sorted by the gender column. So that's the keys in the tables. And again, if you didn't get all of that, that's fine. We'll be going deeper and deeper into this as we go through the indexes. So mentally optimizing the query. We need to join together. The query says, okay, I only want the baby's named Taylor. To find the baby's name Taylor, we need to search through the ref.firstname table, because that ref.firstname table is the only place where first name is in a character value. In ag.firstname by year, we just have those surrogate IDs, right? So we've got to go over here and say, I need to filter out on ref.firstname rows where first name equals Taylor. Ref.firstname is a 4 megabyte table. Now, this is extra information that I've given you. You can figure this out in SQL Server, but it doesn't just like put it in front of you when you're looking at the table in Object Explorer. You have to either go into a report or run a query to say, how big are these tables? So I've kind of just already done that for you, and ref.firstname is a 4 megabyte table. Ag.firstname by year is a 40 megabyte table. So they're both really small, but one is larger than the other. So we are from ref.firstname, we're going to filter rows where first name is Taylor. From the bigger table, we're going to filter rows where gender equals F. Of course, we do only care about the rows where the first name ID matches the first name ID of Taylor, right? So there's 3 things that we're really looking at here. It's a little complicated. So now our challenge is to choose. There are different things you could index here, and I'm going to switch over to Management Studio now, because I do have the problem file up in Management Studio. The challenge is to design an index for this. So let me go, come on, Management Studio. Send Control-Alt-Delete, let's do that. I am running a new Management Studio 2018 that came out today. So if I look at Management Studio, whoop, whoop, this is a preview. So if we get problems from Management Studio, I will be switching back over. This was just released today and announced at Ignite. Now, many of you may be happy to see that if you go into Tools Options, there is, at long last, a dark color theme. This is one of the things that tons of people in the SQL Server community have been requesting. Now, why am I not demoing in the dark color scheme, you might ask? Well, if you notice how muddy this looks, I'm still figuring out things like how to make the highlighting high contrast in it. And if you ask me, it's like Object Explorer, I'm still getting used to it. So I am doing our demos today in blue extra contrast, but know that for you dark theme fans, there is a dark theme there. Many people have asked for that over the years. We are in the file topic 2. If I show this in the containing folder, the file that I'm in, if you are playing along at home, is topic 2 non-clustered key choice problem.sql. And here, what we can do is actually run the query. So over here in Object Explorer, I have the table. So ag.firstname by year, it doesn't tell you it's 40 megs, but it's about 40 megs is this table. We can see it only has that one index on it. So it has that clustered index that's a compound index on report year, first name ID, and then gender. And then ref by first name, it's the smaller one, the 4 megabyte table, and it just has first name ID indexed. All right, so let's go ahead and run this query here. I am in the correct database there. I'm going to go ahead and turn on execution plans. So what I did is I clicked this button right here. This says turn on actual execution plans. There's just boxes and arrows. I don't really know what that means there. But it's this little button. And if I look at my results, by the way, for Taylor's, we aren't ordering our results, but we can see that if we just scroll down a little bit here, some rows, for some years for Taylor, much more popular than other, really came into power in the early 2000s there. I'm not sure, I mean, well, 1992 was a really good year. I'm not sure how much Taylor Swift plays into this or not. But look, on our execution plan, so I switched over here. So since I said include the actual plan, I got an execution plan here that popped up, and this green hint here is saying, hey, Kendra, I'm suggesting an index for it. And I'm going to go ahead and notice it is asking for included columns. It's not a multi-column index, but it's saying here for the key, it thinks that an index should go on ag.firstnamebyyear on the gender column as a key. Now, part of your decision when you design this index is, do you want to listen to this green hint, or do you think there's a better index than you're seeing in this green hint? And I'm going to go ahead and right click on this and say, when we right click, we can say missing index details to see it in a bigger window. So if you want to see the details of this in a bigger window, we've got here, it thinks index on gender and it wants an included column, but we are just trying to do just not includes this time, just one single key column, not the perfect index, but just a really good index. So you could choose to agree with it, or you could choose not to agree with it. So your challenge, let me throw the timer up. And even if you're not playing along with the SQL Server, just write down on a piece of paper or a notepad, either one is fine. What table would you index? Would you index ag.firstnamebyyear? Or would you index ref.firstname? And then, depending on what table you pick, what key column do you think is the most important? So what I'm going to do, I'm going to collapse this right here so I can have it all on the screen at once. So here is the challenge and here is the query, and I will grab my timer. All right, moving the timer over. We're going to do a 4-minute timer, and while this runs, I'm going to try to fix my webcam. So I will mute myself. So I will be back in 4 minutes. All right, so looking at different solutions for this, and if you want to share, oh, awesome. So folks are starting to share their solution. So index on first name on ref.firstname is one guess. If you have a different guess, feel free to put it in there too. So I was looking through planning out the solution. How do we figure this out? So figuring out a solution when there's joins. Oh, this went straight to testing results. So, oh, I see. I have a bunch of hidden files in this one just in case the demo didn't work. So let's actually step through the solution file here. Okay, so I am now going into, and this file you can download from the topic itself to look through the different solution options. This is the solution.sql. We have a vote for index on first name ID on ag.firstnamebyyear as well. Awesome. All right, so looking at, and so here in the what were the ideas, I'm going to put both of those in. So ref.firstname, the first name column, and then ag.firstnamebyyear, the first name ID. All right, let's test them out. So if we can only create one index, and this might seem like a sort of an artificial limitation, but in the real world, we often really want to say, okay, I do want to have a basic amount of indexes to cover all of my queries, but once fairly quickly, we get to a point where whenever we add a non-clustered index, we're adding a copy of the data. And most of the time, we are dealing with tables that are bigger than 40 megs. So every time we add a non-clustered index, we're adding to the size of the database, to the amount of memory it may consume, to the size of our backups, and the database gets bigger and bigger and bigger. So even in the real world, we are often in these situations where we're like, oh, I want to figure out how to make this faster, but I want to figure out sort of the cheapest way I can do it, which means not indexing everything necessarily and kind of figuring out where is the biggest bang for my buck. Now, in some of these tables in here, we might, for this example, we might actually add more than one index, and we'll talk through that. A tool that we haven't looked at yet in terms of figuring out, so you guys didn't have every advantage in this. One tool that I didn't show you, which can really help get rid of the guessing, is this Set Statistics IO On tool. Now, there is some similar information that we can get in the execution plans in more recent versions of SQL Server. So in SQL Server 2014 Service Pack 2 and higher, we can see some similar information to this in the execution plans. This Set Statistics IO On works way back to SQL 2000, SQL 2005, super old stuff that's not even supported anymore. When I turn on Set Statistics IO On, I just get a message that says, okay, I did this. Now, it's just impacting my session. Turning this on is not going to impact people, applications running queries. This is just going to say, when I run queries, put information about how many pages it read into my messages tab. So it might make my query a little slower. There are some cases where observing can slow down the query, but most of the time it's just a very small amount of change. So if I turn on Statistics IO, and let's actually highlight the query and run it, it can, and I do have to use the right database. I've been working on a Windows machine lately, and today I'm on a Mac, so I'm completely confused about which keyboard shortcut to use, Control or the Mac key. So there will be some incorrect keying today. So what I did there is I just hit the execute button after getting into the right database context. I did Control E on the keyboard, which is the same thing as execute. If you are old school and like to use Alt X, or if you like to use F5, I support you, but I tend to do Control E. So this time we got the results, and now that I have Statistics IO enabled for my session on the Messages tab, if we're measuring by reducing logical reads, this will tell me exactly how many logical reads did I get per table. So we did know that the ref.firstName table is 4 megs and that the first name by year table is 40 megs. But now this gives us a number, and these are in pages, the number of 8K pages read. We read 479 pages from ref.firstName. We read 5,291 pages from ag.firstName by year. Now you might wonder, how do we have 479 logical reads and then 0 physical reads and 0 what's called read-ahead reads? Now, read-ahead reads are a special type of physical reads. They use a prefetching mechanism, like a vacuum cleaner that kind of sucks up rows in advance of SQL Server directly needing them. What this means that we have logical reads and none of the others is just that the data was already in memory when I ran this query earlier, and it put the stuff into my buffer pool in memory. And this time when I ran it, it didn't have to go back to disk. Now I have a great question. Why does it show scan count of 5? On ag.firstName by year, it says scan count of 5. On ref.firstName, it says scan count of 1. Let's look at our execution plan and for a little more information there. If I turn on, I'm going to turn on now my actual plans back with this. I could do Control M. I'm just going to go ahead and use the physical button. If I go back into my execution plan, I can see some information that is related to this. In my execution plan, let's zoom in on these operators. Here is ref.firstName, and it is kind of annoying that it, in both Statistics IO and in this view, it's kind of annoying that it doesn't show the schema. We just have to guess from the table name. So here's ref.firstName, and here's ag.firstName by year. Notice the difference between these. This operator has the double arrows on it. This operator used multiple cores. I have 4 logical cores on this virtual machine. If we go into some of, I'm going to right click here and say properties. Oh, interesting. It kept the properties in the dark theme. This is a preview version of SSMS, and apparently it likes to kind of certain things from that stick around. Now, I like to manually move my properties button over to the left, or properties tab over to the left, just because I use it so much. I like to drag it over there. It's just a preference. But one thing we can see from here, notice that we have parallel is true here. So it's talking about how parallel it was. And I actually want to see the number of threads on it. Let's see if it'll show me that or not. Yeah, let's do actual IO statistics there. So this is part of the information. Let's zoom a little. This is part of the information that will only show up in execution plans on on more recent versions. I believe it's SQL Server 2014, Service Pack 2 and higher. And to get it, it's not just the version of Management Studio. The SQL Server instance itself, in order to include this in an actual execution plan, it has to be that version or higher. But if we are on that version of higher, it will tell us in an actual plan, this went parallel. So here's my 4 CPUs that actually did, each of them went and brought the data in on the ag.first name by year. So there's 4 of them that actually did work. It allocates another thread that watches them and is like, are you done yet? Are you done yet? Are you done yet? And it actually did show a little bit of IO on that thread, but that thread is really, it's called a coordinator thread sometime. So that's why scan count, when you see scan count of 5 in an indication there, it generally means that it went parallel, and the number in the scan count, maybe it's related to your max stop, but then it also includes that coordinator thread. This is also an indication, right? So this is our, notice this is 5291 is what's showing there. Back in our statistics IO, it also, so it matches 5,291. The good news is our execution plan agrees with our statistics IO output that we had to read 5,291 pages from ag.first name by year. The ag.first or ref.first name table, on the other hand, notice that it didn't go parallel. That's why it had scan count of 1. It just used 1 little core for this. It did have to, because part of the plan went parallel, so because this guy has, you know, parallel operators on it, and it wanted to use parallelism for other things. We now have a distribute streams operator here. This guy was single threaded. So in order to combine the results from 1 core with everybody else, it actually has to distribute it so it can now use multiple cores to do this bitmap create. We'll talk more about what bitmap create is in the next session, or the next lesson on this guy. So we will decode that guy soon. Now we have figured out the logical reads, and we just went ahead and did this part in the execution plan where we can see, and this is it. So SQL Server 2016 plus and SQL Server 2014 SP2 and higher. So the good news is my memory on the version was right there for seeing IO statistics in there. Sometimes my memory on this service pack number isn't so great there, but this time it did okay. So how do we pick one index for it? My first instinct is to usually look at the, now, and this can, sometimes we can't run the query, right? Sometimes the query might take an hour to run, and either we're not allowed to run it or we don't want to wait an hour. So if we can't run the query, one thing that I usually do is look at these different tables that are involved, and then start looking at, okay, how big are these things, right? Either by using, we can use custom queries for this, and we do have some of these that you can look at in here, or we could go into the report. So I highlighted the database name there. If I do the reports and I do the standard reports, I can do disk usage by table. I'm going to do disk usage by partition just for fun. Sometimes you have partitioned objects, sometimes you don't, but notice that it doesn't just, every table has at least one partition. So I do still have info in disk usage by partition for objects that aren't using table partitioning. You still get it in there. And I can see that the ag.firstnamebyyear table has one index on it. And here I can see, hey, it's about 40 megs, right? So if I can't run the query, I want that information for, okay, about how big are they? I can see that ref.firstname down here is about 4 megs. It's in fact under 4 megs. You could also just run queries to get this kind of information as well. If you expand this here, you can see the number of partitions. This is not using table partitioning, so the number of partitions is 1. So that report will work there too. If we can run the query, I like to use those logical reads in the statistics IO output or in the execution plan. So that the fact that I'm doing more logical reads against the ag.firstnamebyyear table, it's 5,000 of them. The fact that I'm doing that, and the fact that it's using parallelism for that table too, now that I've seen the execution plan, that makes me think, hey, this table is going to be more likely to give me more bang for my buck if I index the table that has more logical reads. But which column? Well, we've got the join column is an option. And then we've got the predicate column is an option as well, because on ag.firstnamebyyear, we need to limit it down to the right first name ID. We need to find only that whatever the first name ID for Taylor is. And then we need to figure out only the babies that are girl babies. So if I have to pick one column, which should I pick? And let's remember, if we go back to that execution plan, which I still have here, SQL Server seemed to be suggesting gender, right, in its little index recommendation there. Well, if we're going to think like the optimizer, not like the green query hen, but if we had to run this query ourselves, which of these is likely to narrow it down to a smaller list? Are there likely to be, is the babies named Taylor of both genders going to be a smaller number, or is the number of female babies of any name going to be a smaller number? Well, we know that our data set is about United States data, and we know that in the United States, roughly half, maybe a little bit more, of the babies are girl babies. So narrowing it down to only girl babies is going to maybe cut our set roughly 50% in half. We're still going to have about 20 megabytes of data because we know this table is about 40 megs. How many babies are named Taylor? Well, this again, we do have to kind of know our data set a little, right? Because if we were from another, if I wasn't from the United States, I might wonder, could 50% of the people in the United States be named Taylor? Well, I do have to have a little knowledge, right? But I actually think it's going to be much smaller than 50% because I just don't know that many Taylors. So I am going to guess that baby is named Taylor. This is the first name ID criteria because we don't have first name in that table. It has the surrogate column. I'm going to guess that that is going to narrow it down more. Let's look a little bit more now before I malign SQL Server too much. I do want to show you a secret about that index hint. This index hint, you're like, if I look just at this index hint and I right click here like we did before and I look at the missing index details, there's just one index in here, right? I just scrolled down. There's one index in here and it's saying just narrow it down to 50%. And then it's saying include the name count column. Notice that first name ID is nowhere in this index. Nowhere in this index. Kind of dumb, right? Well, it's just the display is more dumb than anything else. If I go into the properties of this plan, and I have to click to get it to show me actual properties of the plan, notice that there's along here, I've highlighted the select operator. There is a missing indexes info thing. I'm going to expand this using the plus here. Expanding this, hey, wait a second. There's 2 missing indexes. The green hint will only ever show you one of them. The green hint has an impact here. What it means by this impact is it thinks that the index it's showing here is likely to reduce the estimated cost of the query, which I can view on the select operator. It's likely to reduce this cost. So cost is just a guess at how expensive is this query. It thinks, oh, I could reduce that by about 38.5%. Let's look at what our cost number is. Our cost number, cost is always an estimate, is 8.58. So it's like, oh, I could reduce the cost of 8.58 by like 38%. Now going back over here to our missing indexes, notice that missing index 1, hey, that's the one we saw there, 38.5%. But notice that there's a second missing index here that it actually thinks would reduce the cost of the query by 93%. It just didn't decide to show us that in the green hint, and it can only ever show one suggestion here. It can only script one out to missing index details here. But if you look in the properties of the plan, you can quickly figure out, is there more than one? And I'm just expanding out the index details here. It doesn't display it very gracefully, but we can see it in the properties. So there is another index that it thinks would help. It is an equality-based index. It thinks, oh, I need to expand column 1. Here we go. It thinks that it should have key columns on first name, ID, and gender. Hey, this is kind of a duplicate to the other index. And then it thinks that it should include the name count index. And it thinks that would reduce the estimated cost of the query by 93%. You can also see these by saying, hey, I want to see the XML of the execution plan. And if we look at the XML of the execution plan, and then we do, I usually even, they're kind of at the top here, but they aren't always. So you can do find and just look for the word missing, right? So I just brought up, it's not zooming very well. I just brought up the find thing and looked for the word missing. That'll generally take you right to the missing indexes. And now I can see, oh, here's one missing index that wants an equality. It wants a key column on gender and it wants an include on name count. I can see its impact. Oh, hey, there's another one that it actually thinks would help a lot more with 2 key columns on first name, ID, and gender, 1 key column on name count. Now, one thing here, when you see an index suggestion in SQL Server and it is suggesting 2 key columns, it has not done any analysis about which column should come first. So it put first name ID first in this index. It put gender second. It has no idea if that's better. When SQL Server makes these suggestions, it's making them in the time it optimizes the query. And it's trying to optimize that query really, really fast so that you can start running it. So it's just like, yeah, maybe these should be in the key. I don't know, go. It's just telling you, I think you should think about an index like this. It is suggesting, I mean, there is no reason we should have both of these indexes in there. It is over suggesting that is common for it to do. So you want to, when you see these requests, you want it, when you see the little green hint, first up, do not assume that's even the most important index it's suggesting, right? It actually thinks there's another index that would be way better than this. So don't even, I mean, the first thing to do is say, hey, in my properties, is there more than one of these? Right? Because if there's more than one of these, this one may not even be may not even be relevant or worth looking at. Because I want to even, and also it's completely guessing. So let's go ahead and create that index on gender. But first, getting too ahead of myself. So that green index hint there, we can also see in SQL Server's dynamic management views, aka DMVs. So now we're going to query these. These are in individual databases, right? Because I could have very similar or identical schemas in different databases that have different database names. So at the database level, SQL Server tracks these missing index requests in multiple DMVs. We've got index groups, index group stats, index details. And you'll see lots of tools looking at these DMVs to suggest indexes for you. Everything from free tools like Brent Ovazar Unlimited's SP or First Responder Kit to monitoring tools often look at this, all sorts of different tools. Glenn Berry's scripts from SQL Skills, all sorts of people look at these because they give advice on indexes. And notice that we see both of these in there. So the one that showed up in the query, in the little green hint in the query where it can only display one, it was the one on gender. The one that was hidden that we could only see in the execution plan properties in XML is the one on first name ID and gender with name count as an included column as well. And again, nobody has done any analysis on the order of these columns. This is a documented limitation of these views where even in the documentation, they're like, yeah, it's up to you to determine the order of these. We are just listing the columns that we think might be useful in the key. Maybe, maybe, right? Here we can see this is the impact. I've just labeled it average estimated cost reduction to try to make it more clear. The times requested is just I've run this query 6 times. So they've shown up 6 times. That's what it means. Times requested is the number of times this query has been executed, not compiled, actually executed, is showing up there. Now these will get cleared out. If I take this database offline and then bring it back online, these are gone and they only start piling up again as queries run. If this fails over in an always on availability group, same thing. If you turn the instance off and on, if your failover cluster fails over, they get cleared out. Also, as we'll talk about later, certain things like maintenance or like creating indexes on the table are going to clear them as well. They are very temporary. Now you may have another tool that you may have a monitoring tool that's persisting them over those things, but I'm just talking about querying them directly. They get cleaned out pretty frequently. All right, so the index that SQL Server suggested, let's go ahead and create that. Right now, I'm violating our rules. Our rules were that we wanted to create a single column index that did not have an include. But just to give SQL Server an advantage and to test out what it suggested. Now, none of us actually suggested this index, but SQL Server suggested it. We're going to go ahead and create it. And we're creating it with what I like to call the name of shame. This is when you find an index that has this name of missing index, comma sysname, right? That is exactly what, if you script out the little index, that is the index it's suggested there. And you can create that as a name, but when you look at it, you know that someone was in a panic. If you find this, that someone was in a panic and they just right-clicked that hint and were like, create, without even looking at what it was named. So, may have been guilty of that at one point in my life, but it is the name of shame. So I've now created that index with the name of shame, which we all do at one point, maybe not all of us, but a lot of us. And let's see if our query is going to use it. I do not have to, like when I create an index, I don't have to clear out the execution plan cache or anything like that. By creating this index, a couple of things have happened. Well, one thing that happened is if we go back up and look at our dynamic management views and say what indexes have been requested against this table. This is the same query I ran before. Notice that all of my DMV data for this particular table is gone, right? I haven't been querying. This is just looking at our current database. I haven't been querying other tables. And that makes sense because if I create a new index on this table, it needs to re-optimize all the queries because the queries may decide to use it again, right? Like the old suggestions may no longer be valid. It also, when I created this index, went into the execution plan cache and figured out, I mean, everybody who's using this table, everyone who references ag.first name by year, their plans are invalidated, and the next time they run, they need to get a new execution plan because the indexes have changed on the table. So I do not have to use a recompile hint or anything to see if my query is going to use the new index. I can simply rerun my query and see, hey, do you use that new index? Looking at my execution plan, SQL Server is still asking for an index, but things have changed in my query. We are still looking at ref.firstName by year, but instead of a clustered index scan, we now have an index seek on it. Now, this is interesting because we're taught, when we first think about indexes, we're taught that seeks are good and scans are bad. So we are, let me get that tooltip out of the way and resume. Over on ref.firstName, we are still doing a clustered index scan, but we are now doing an index seek on a non-clustered index on ag.firstName by year. And we're taught that seeks are better than scans, but we're doing a seek on a 40 meg table. We're doing a scan on a 4 meg table. So seeking on a 20 meg table, exactly how much are we reading? Because we're only, if we look at our properties here, and we look at our actual IO statistics, we are still doing 2,705 logical reads, approximately 50%. We had what, 5,000 logical reads before we did this index. We are seeking on, I can go down here and look at what are our seek predicates. We are seeking on, if I pop this up, our seek keys is just gender equals F, which is about half of the rows. So yeah, and this is the thing about seeks is I've seen seeks that are actually reading the entire table. This one's reading 50% of the table. The difference between a seek and scan isn't always that important. It's because with a seek, we still want to know how efficient is the seek. And seeking down to just these girls, even though we, come on, let me click on the other tab, SQL Server, it froze up a little there. Even though we're doing a seek, we are still, and this is just the same information, different format, we are still doing 2,705 logical reads. So we've gotten this down to about what? 3,200 logical reads total. So we have reduced the amount of logical reads, but it isn't that awesome. So let's see if we can beat SQL Server. I'm going to drop the index with the name of missing index sysname. And now let's create this one. This one was suggested by Devin. We're going to index first name ID on ag.firstname by year. So now I dropped, I'll just make sure I actually, yep, I did drop it. And we've created the new one. So now that I've created that one, let's rerun our query and see how this does. Looking at our execution plan, hey, things are quite different. We no longer have any parallel operators anywhere. Now, SQL Server is still asking for an index. We'll look at that in a minute. It may be looking for more than one, right? We don't know. It's looking for, when you see the green hint, it's looking for at least one index, a minimum of one. But it was able to, the overall estimated cost of this query went down enough that compared to our cost threshold for parallelism, it decided, hey, we don't need to go parallel on the operator that accesses ag.firstname by year. Now, our index isn't perfect because we can only create one single column index. So it's actually accessing ag.firstname by year twice. We're doing an index seek here and we're doing a key lookup here, but we're doing them both with single threaded operators. Now, how many rows are coming out of this guy? I'm going to highlight on the index seek here. This is at the bottom of a nested loop operator. It thinks I'm only going to have to run this once. With a nested loop, we might have to go through it a bunch of times. I'm only going to have to do it once. And I think I'm going to actually get 11.7 rows back. We'll always get a whole number. And I think I'm going to have to read a few more rows than that. I think I'm going to have to read maybe 20 rows, right? But there's not a lot of tailors, it doesn't think. Now, the actual number of rows was higher than the estimate. The actual number of rows was 63. It had to read 201 rows to find those rows, but it's pretty close, right? But this is not a lot of rows, right? How many times did it have to do this key lookup? This key lookup over here was executed 63 times. It returned 63 rows. Hey, that's not bad. So we basically had tailors in, if we look at our row count here, there are 63 rows. So that we had tailors who were girls in 63 different years. Well, how many logical reads did that end up being? Because we're trying to measure by reducing logical reads in this case. If I highlight the select and I look at my, let's find it. Here's the query time stats. I want the IO usage. Oh, I'm looking in the wrong place. So on the select operator itself doesn't do IO. When we're looking at execution plans to find how much IO was done, it's broken down by operator. So I need to go over to ref.firstname. I can see that the IO statistics for ref.firstname was 479. There we go. Awkward zoom. The IO statistics for this index seek was 3. Here's my 3. And the IO statistics for this was 189. So 189 plus 3 is 192 logical reads for ag.first name by year. If we go back here, ag.first name by year shows up with 192 logical reads. And now everything is scan count 1 or scan count 0. This work table, what's the work table? That's interesting. What is the work table in this case? So work table is generally, hey, I had to go do something in tempdb. So typically we can find a sort operator or a scan or not a, we would find a sort operator or maybe a spool operator that did it. We just have nested loops and key lookups here. So I'm actually, I mean, it didn't do anything. If we look at this, logical read 0, like it literally didn't do anything. I am interested in why it showed up in the execution plan at all. Oh, so question, can I see the clustered index on ag.first name by year? Sure. So let's go ahead and I'm just going to script this one. So the clustered index on ag.first name by year, the first column is report year. The second column is first name ID. So this means everything is sorted first by report year. If we are looking for first name ID equals 2, if I just look at, so I'm going to do select top 100 star. I'm going to order by report year first name. I'm going to order by the key columns just to make sure, because I'm not guaranteed order unless I order by something. So if I select out of here, right, everything is ordered first by 1880s, then by first name ID. So if I'm looking in here for I want the rows where first name ID equals 2, it's like, well, it might be in 1880, it might be in 1881, it might be in 1882. I'm going to have to scan the whole table because everything's ordered primarily by report year. Is the primary sort column. First name ID, if I am specifying a report year, I could seek to first name ID because I could be like, oh, report year is 1880. I could go straight to that first name ID. Okay, so the reason that I'm asking is, shouldn't your non-clustered index have these keys as hidden columns? Yes, so there is a secret in our execution plan. Let me go back to that other window. There's a secret, in fact, that I glossed over in our execution plan that we are going to look at later. In this index seek here on ag.first name by year, if we look down here, the seek predicate is on first name ID equals scalar operator because we created an index on first name ID. Remember, we created a single column index on first name ID, and our index is named IX1 column even, right? So this is absolutely the index I just created. The seek predicate makes sense, right? It's seeking on first name ID. There's something up here that I didn't discuss when we looked at this object. There is a non-seek predicate on this index as well. So we can have things that we seek on, and then we can have filters. If you see predicate without the word seek in front of it, it means I looked at every row and I applied this filter. I couldn't narrow it down and go straight to some rows. I had to do a filter. And it's somehow able to do a non-filter predicate on gender equals F, even though we didn't explicitly put that column in our one column index. And that is because the columns from the clustered index are secretly used in the non-clustered index in the background. And it did actually use it a little bit to help this query out. Yeah, and we will dig deeper into that later. The big reason that this index was able to make things faster, though, is absolutely the seek predicate on first name ID, which is the column. When we specify, hey, we want our key to start with this column, that is always honored. So SQL Server may sneak columns later in the index, but like what we specify as the key columns are kept in that order, and we always, that is honored. And that's really what made this index powerful. So yeah, there is more secret stuff in the index, but we specified the part that actually made it really fast. And if you've got more questions, but yes, I did kind of sneak past that. I promise we'll talk more. All right. So yes, our single column index is more complicated than we thought. So I am going to drop this index, and now I'm going to go ahead and create an index on, if I go back to the top real fast. How is it 9:25 already? Time flies when you're talking about indexes. I'm going to go back up to the top. And we want to create an index on ref.firstname on the first name column. So let's create, oh, look at that. That column is not properly terminated. We're going to create index ix ref first name on ref.firstname first name. Here we go. So let's check this guy out. And query completed successfully. And now, and the truth about this index on ref.firstname is ref.firstname is a small lookup table that helps us decode the first name. Now, this is not a ton of logical reads. It's only 4 megs. And yeah, it's a small table. The truth is I would probably index this just if this is going to, if we're frequently going to look up things based on the first name, yeah, this is worth indexing, just because why do a scan there repeatedly when a non-clustered index is small? So I'm not saying this is a bad index at all, but if we have to choose just one index, how much did it speed us up? Looking at our statistics.io, and I actually do need to run it with statistics.io to figure out, let's run it again and look at the statistics.io. This one actually turns it on. This does get us down to 2 logical reads on ref.firstname, but the bulk of our logical reads over on ag.firstname by year is still 5,200. So if I had to pick one index, I would choose an index on ag.firstname by year, just because it's bigger and narrowing down the logical reads there is the biggest bang for our buck. But honestly, in the real world, we would probably also index ref.firstname, and we would want really efficient seeks on both of these tables, because that ref.firstname table is probably going to get pulled into a lot of queries. All right, so somehow my SQL Server 2014 query completely ignored the index. Oh, interesting. Let me take a look. I'm going to create it just with your exact syntax. So let's talk about why this can happen. So sometimes when we create a narrow index, let me drop this guy. Actually, I'm going to leave that there for a second. I'm going to leave it there for a second. That's fine. Stay there. I'm going to paste this in. Let's create test2 on ag.firstname by year. And now let's rerun our query. And with both of those there, let's see what SQL Server does. Decided to use it on my instance. The question is, hey, on my instance, it decided not to use this narrow one. I'm now going to go ahead and drop the small one. Let's drop this. And to drop it, I can't include the key list. There we go. So just highlight part of it to get it to drop. And now let's see if it will use it. On mine, it is still using it. But so the SQL Server Optimizer does change between different versions. In my version of SQL Server, let's go to the properties of my query. I am using, and you may be using the same or different. It actually, one thing that plays into this though, is our cardinality estimation mode. So my query is using what's called version 140 of the cardinality estimator. I'm going to change that and see if my query changes behavior. It might not. Let's go ahead and it's all about how SQL Server does estimates. And this can change with major versions of SQL Server as well as with this setting. And this is important to know because sometimes when SQL Server just has an upgrade, it may change the way it uses indexes because the cardinality estimator has changed. So I'm going to go into options here and I'm going to change, actually on this one, I'm going to leave my compat level the same. Used to, this was only controlled by compat level, but now I have another option to control it. It's kind of heavy-handed to change your whole compat level because that can change a whole host of settings. Now I'm on SQL Server 2017 here. I have an additional option where I can just say legacy. I want to use legacy cardinality estimation. So I don't have to change my whole compat level, but I'm going to use the old, what's called the old cardinality estimator. And this can change some of that behavior. We'll see. So I'm going to script this to the clipboard, click cancel, just so I can easily undo it without having to go back in there. So now look at that. They're so inconsistent, bless them. They didn't capitalize everything. That's so weird. I don't even know if it's going to work. It did work. Okay, so now we don't have to capitalize on, I guess. They're really Oh, bless them. They're so inconsistent, but at least they get it done. So now, oh, it's still choosing to use it even with the legacy cardinality estimator. Sometimes changing that setting can change it too. So let me switch this back just so I don't have that set for the rest of my demo. But what we're going to talk about, in fact, in the next module is what can influence this choice, because what's happening here is my instance is it's looking at these estimates. And the question for SQL Server is it worth it for me to access ag.firstname by year twice or not? And my instance is deciding, yes, it is. But not every instance will decide this depending on the data that we're looking at. And we are actually, in fact, in the next problem, going to dig more into that. So we'll dig more into why that is in the next problem, because I can't always just create a single column index that covers part of the query. Like in our case, my single column index only addressed the join criterion. That was singular. It didn't address any of the others. And sometimes that's just not enough in every version of SQL Server. So that brings us perfectly to problem number 2. All right, so let me bring up problem number 2 here. Now we have been going actually for 90 minutes. So let's go ahead and take a 7-minute break. I find that this class works a lot better if I give people time to like check their email and get up from their desk and get coffee between things. So we are going to meet back in 7 minutes, and then we are going to dig into topic number 3, which is keys versus includes. So I'm going to go grab some water myself, and then I will be right back.